Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course being conducted by Department of Mechanical Engineering, Guwahati under the NPTEL program. And it's a 12-week course, and we are into the 11th uh, week of this course. And the topic of discussion in this week's content has been measurement diagnostics and experimental facilities for compressible flow. So basically, how we measure properties in our compressible flows and how we analyze it experimentally. So that is the focus of discussion in this week's content. Instructor for the course is Professor Niranjan Sahu from again Department of Mechanical Engineering, IIT Guwahati, and I am a teaching assistant for this course. Also, a research scholar here at Mechanical Engineering, IIT Guwahati. So we shall wait to see if somebody join. After that, we can continue with the session. Thank you. Okay, so we can start with today's session. So three lectures are there in this week's content. Lecture number 26 to 28. So lecture number 26 focuses on pressure measurements, temperature measurement. Okay. Lecture number 27 discusses your density variations, how we capture density variations. And then lecture number 28, there are experimental facilities that are used to study our flows. So this is there. So week number 12 also is on the same topic. So half of the topics will be covered in your week 12, if I remember it correctly. So lecture number 26. So these are the topics: measurement challenges in compressible flow, temperature measurement, your Prandtl number, adiabatic wall temperature, adiabatic recovery factor, probe recovery factor, and pressure measurements, measurement of flow velocity. So these are the topics. So in your this topic, measurement challenges, basically when we talk about compressible flows, we are mainly focused on the density variations. So how we can capture those density variations, that remains the focus. So through the pressure and temperature variations, we can do it. Okay. Then there are optical methods also by which we can do that. Right. So in your temperature measurement, so this thermocouples have been discussed and how they function, right? So Seebeck principle for thermocouples. So the principle says that flow of heat in a metal causes your electromotive force, EMF, right? So based on this principle, the thermocouples are designed. Then your what is Prandtl number? Prandtl number basically is your dynamic viscosity to your this acoustic speed, right? So this basically is the measure of your effect of your fluid friction to your dissipation, heat dissipation. So which factor will weigh more in what conditions? So this basically is your Prandtl number. Then adiabatic wall temperature is that if you are the flow is happening on some surface, right? And that surface we keep insulated. So the pressure it experiences, sorry, the temperature it experiences is the adiabatic wall temperature, right? So these adiabatic recovery factor and probe recovery factor basically are to measure that how accurately we can get the actual temperature measurement. Okay, so this is there. Then pressure measurements are there. So two types of pressures are there. One is your stagnation pressure, one is your static pressure. The pressure, so let's say flow is happening in a conduit. Okay. So there are two pressures involved here. One pressure is that this wall is experiencing. Okay. And one pressure is because by virtue of the flow uh, of the fluid, right? So this basically is at the walls. This is your static pressure. Okay. And because of your velocity is your dynamic pressure. And then there is stagnation pressure, which we often call as total pressure. So what is total pressure? Your total pressure basically is your static pressure plus your dynamic pressure. Okay. Now to in subsonic flows. So we have this Prandtl uh, pitot static tube. That is used to measure the flow pressures. So both the stagnation and your static pressures. Okay. So it is something like this. So this here will give you total pressure, stagnation pressure, and from here you will get pressure here. Okay. So this is going to give you static pressure. That is pressure at the walls. Why stagnant? Because at this point, your flow is going to stop here, right? So stagnation condition will be uh, achieved here. So that is going to give you your stagnation pressure. So this is there. All right. Now this was for your subsonic speeds. So for your supersonic speeds or supersonic flows, so what happens is that you have flow is happening in this direction, but in front of your this pitot tube, you are going to get a shock. Okay. In that case, let's say this was region 1, this was region 2. Here the pressure was P naught 1. Here the pressure will be, behind the shock will be pressure, total pressure will be P naught 2. Right. So when we are going to get pressure based on this pitot tube, so this is going to give you information related to your P naught 2. And then there are ratios related to it. So that you can see in your lecture slide. Right? So this is there. Now, if you want static pressure here, so how can you get static pressure? So on the walls again, you'll have some sensor on the wall that is going to give you your static pressure. Right? So this is there. Now, flow velocity is there. How we are going to calculate flow velocity? So in your subsonic speeds, you have total pressure. Okay, you have static pressure, and you can find out dynamic pressure. Half of rho v square. Yes, this we can find out. And if we know the density of the flow, we can calculate this flow velocity v can be calculated. So in your supersonic speeds, based on the pressure ratios, okay, P naught 2 by some static pressure ratio, you can get your Mach, right? So this is about the topics that have been taken in your lecture number 26. Then we will move on to questions. So again, based on your lecture slides, these questions are there. So one by one, we will see these questions. So first question is there. Please read this question and try to give an answer. First question says that the pressure gradients can only lead to change in the velocity of the flow and not its density. So fundamental question. This is false statement. Okay. Pressure gradients do lead to change in your density. Okay. So question number two then, please read the question and try to give an answer. So this says that the total temperature in a flow is measured by a device without disturbing it. So this talks about total temperature. So when we talk about properties, total properties, be it your pressure, be it your temperature, right? So we'll have to get into the flow. If you see, when we were talking about pressure, right? So we'll have to get into the flow. Okay. So eventually, what happens is you'll have to disturb the flow, right? Because you are putting some probe into your flow, right? If you are measuring a static property, right? So the probe or the sensor will be on the wall. In that case, you need not to disturb the flow. But here, you will eventually be disturbing the flow, right? So false statement. So this is there in experiments. If you compare the experiments and you see it along with your computational numerical methods, right? So in numerical methods, you can get your whole flow field as it is, the whole flow field you can get, right? But in experiments, you'll have to weigh, right? So what amount of intrusion you can have in your experiments, or what amount of intrusions you can uh, is okay for you for your study, right? So this you'll have to take a call, whichever uh, flow you are trying to study. Okay, so this is there. Then third question is there. Third question says that a thermocouple is based on which of the following options? So four options are there. So I've already told Seebeck principle. Okay. So you'll have one metal. Okay. Then some other metal you'll have. This will be giving some potential. Okay. So here you are heating your metal this way. This is metal one, metal two. So this was question number 3. And fourth question is there. Please try to give an answer to this question. So question number 4 says that in a thermocouple, one junction has the temperature to be measured while the other has a known temperature value. So whether this is correct or not. So this is a true statement, right? In one junction, your temperature you have to measure, while in the other hand, you have known temperature value. So this is there. Okay. And Seebeck principle you use in thermocouples, which basically says that when heat flows through a metal, so you get a EMF there. And fifth question, please read this question and try to give an answer. So this information is based on your slides. So the question says that which type of thermocouple is developed using chromal and constantan? First option is E-type only, second option is K-type only, third option is T-type only, fourth says that both A and C are correct. Sorry. So chromal and constantan. So this is E-type thermocouple. Okay. So correct answer is A. So this is a good question. So please try to answer this. So based on your Prandtl number, so the numerator is related to your friction, right? Viscosity, and your denominator is related to your dissipation. So it says that when the Prandtl number is low, the temperature observed by thermocouple is higher than the actual temperature. So whether this is a correct statement or not. So if your Prandtl number is low, what does it suggest? So it suggests basically that your thermal dissipativity is, which is in the denominator, is going to be high. Yes. So now your dissipation, if it is high, in that case, your thermocouple is going to give a higher than actual value or lower than actual value. So this is going to give a value which is lower than the actual value, right? Because dissipation is high, right? So in that case, this is a false statement, because here it says that the temperature observed by thermocouple is higher than the actual value. So this is a false statement. So moving to the next slide. Then in lecture number 17, so regarding density variations and how we capture in our compressible flows, this has been discussed. Okay. Then about your optical instruments, discussion has been done. Yes. And then Schlieren apparatus has been discussed. Shadowgraph technique has been discussed. Interferometer. Then at last, electric discharge flow visualization. This has been discussed. So in your density variation techniques, Schlieren, shadow graph, and then interferometer. So this has been discussed. Okay. So what is the principle? So three measurable quantities are there. One is temperature. Okay. So because these are optical instruments, so this has to do with light, right? So one ray is there, second ray is there, right? So one ray is passing through one region, second ray is passing through second region, right? And densities in these regions are different. And these differences are going to give you these measurable quantities, be it your temperature, this time difference, be it your angle difference, right? Or be it your displacement. So in case there was no density variation, when where was the ray? And in case there is density variation, now where is the light ray? Okay, so what is the displacement? So based on this, density variations are mapped, right? So your interferometer works on this. DT. Slaren works on this, and your shadow graph works on this. So this is there. So your Slaren setup is like this. So this is the direction of light. Okay. This is knife edge. These are light rays, right? Then this is screen. Okay. So the flow you are interested in is in this region. Okay. The light will pass through it. So then after passing through it, it is going to get into this lens. From this lens, this is going to project onto a screen. So this basically is the Schlieren setup. Now, what is the purpose of your knife? So half of the path you're going to hinder with your knife. So what will happen, because there will be density variations, right? So there will be density variations, and because of this density variations, you are going to the ray of lights. So if normally it was passing through some path, so because of density variations, this light ray is going to change its path, right? And when it has changed its path, so this knife is going to hinder some rays, right? And then you are going to get some dark patches uh, on your screen, right? And these dark patches are basically because there is refraction in the rays because of density variations, right? This way we can use this Schlieren setup to see how the density is varying, right? So here, first point is this is first derivative of density when we talk about the density change. So the variations that I was talking, we see on the screen. So this is your first order derivative of your density. Okay. And this is preferred when your refractive index changes gradually. Okay. So this is about your Schlieren setup. Now what happens in your shadow graph technique is that you have a light source here. Okay. Then you have a lens here. Yes. So from here, from this light source, you'll have your light rays, right? And here you'll have your flow that is happening. Okay. Test section or you call. Then here you're going to have a screen, right? Now because of again density variations, right? There will be refraction, change in path of the light rays. So now, before this density variations, what were the intensities on the screen, right? And after the density variations, what are the intensities on the screen? So through this difference, we try to get the density variations, the change in the intensity of light. Okay. And this is so these variations in illumination are proportional to second derivative of density. So this is there. So where there are high gradients, right? High density changes are there, like there in combustion. So where, so there in those situations, we use this technique. Also, if we compare the Schlerin and shadowgraph technique, so shadowgraph technique is less costly in terms of its setup. Okay. In same way, we have interferometer, right? So light passing through two same rays passing through two different regions. Okay. Now, eventually they'll meet at one place. So interference is going to happen and fringes will form. Okay. Now, based on the displacement of so if they are passing through same regions, right? And if they are passing through different regions, so there will be differences. And based on these fringes, we can find out the density variations in your interferometer. So this is there. So this is there. So your shift in the fringes can be recorded by taking the photographs with and without the flow. Okay. And it is then correlated to the equivalent change in the optical path and subsequently to the change in density. So this is your interferometer. Then same way electric discharge flow visualization is there. Okay. For your compressible flows. So this you can check through your lecture slides. Okay. And we'll move on to questions. So this is the question. So please read this question. So the question says that variation in density of gas stream produces a corresponding change in the refractive index of the gas. So this is true statement. Okay. Change in density is going to change in the refractive index. And because of this change in refractive index only, the path of light changes. Okay. And which your optical instruments eventually exploit this behavior only. And question number 8, Schlieren apparatus is useful in studying the density gradient by measuring the displacement of light of the light ray. So whether this is right or not wrong. So Schlieren basically works on your deflection angle. Okay, not displacement. In that case, this comes out to be a false statement. So whether this is, in the last question only I have told that deflection angle change is used in your Schlieren. But in interferometer, what do we use? We use this dt. Okay. So between two rays, so this dt information is used. You can see this on slide number 19 of your lecture number 27. Right. So this becomes a false statement in that case. Then question number 10, whether this is correct or not. Please read the question and try to give an answer. So it says that Schlerin technique can give a quantitative estimate of density gradients in the flow field. So we have seen that the Schlerin technique gives your density gradients of your first order, right? So though it gives qualitative data also, but it can be also used to give quantitative estimate if proper calibration is done. So this should have been, I believe, a true statement, but then I'll again check it if the answer is otherwise, but it should be a true statement, right? Schlerin technique. Then question number 11 says that in your shadow graph technique, the variations in illumination of the picture on the screen are proportional to the first derivative of density. So we have seen that this is your second derivative of density. Okay. In that case, this becomes a false statement, right? So this is about your question number 11. Then we have lecture number 28, last lecture. But before starting this lecture, we are going to take a short break. After that, we will continue with the session. Thank you. Okay, so we can continue with the session. Then experimental facilities. So this has been discussed. Okay. So subsonic wind tunnel is there, then wind tunnel instrumentation is there. So this is there. After that, so this is from previous heading. So this is there. Okay. So in this week's content, subsonic experimental facilities. So this has been discussed. So lecture number 28. So one categorization has been done. Okay. So this okay. So this is there. So beyond your hypersonic flows. So this is hypervelocity flows. So this is one category in your flow regimes, right? So your subsonic, transonic, supersonic, hypersonic, and then hypervelocity. Then there are types of facilities. One is your open circuit, then is your closed circuit. Open circuit, closed circuit, as the name suggests. So let's say you have some uh, wind tunnel, be it your subsonic wind tunnel and supersonic wind tunnel. So the tunnel will be in such a fashion that you'll have flow coming here, flow going out from here, right? Now, if the tunnel is in has been designed in such a fashion that the same flows keeps on going in it, So this is basically a closed circuit wind tunnel. Obviously, it will have its sections, right? So this is there. Now then, talking about your yes. Then there is suction type and your blow down type. Now, what is this suction and blow down? If, let's say, this is your open circuit tunnel, if the direction of the flow remains same, right? Let's say somewhere here you have your test section where you are going to study your flow. You'll have some model placed here, and on that you want to study its flow physics, right? Now, if you have some fan here at this location, right? So basically you are blowing down this flow. And in case you have fan in this direction, in this at the end, so basically you're sucking in your fluid or air. In case of a wind tunnel, it's air, right? So this is there, okay? Suction and blow down type of tunnels. Then a subsonic wind tunnel, if we talk about. So this is your settling chamber. This is your contraction zone. This is your test section. This is your diffuser. This is your drive section. So this is suction type of open circuit suction type of wind tunnel that we have in our wind tunnel lab here at IIT Guwahati also. So this is drive section where you are going to have a big fan. Okay. So this is going to suck in your air. Yes. And then this is your settling chamber where the air settles. Also, we want the flow to be well channeled. Okay. So to minimize, we want the turbulence to be minimum. Okay. So in settling chamber, basically we use honeycomb structures, right? So that your flow straightens and your turbulence reduces, right? Then at your contraction zone, the flow speeds up. Yes, the flow speeds up and enters the test section. Now in test section, you can keep your aerodynamic body. Yes, or in case it's a water tunnel, hydrodynamic body, and then the flow on it, how it behaves. So this we study. Yes, and then eventually your flow enters the diffuser where the flow diffuses. Okay, its velocity reduces and then it exits the wind tunnel. So this is your subsonic wind tunnel. Then wind tunnel instrumentation has been discussed. What is there in wind tunnel instrumentation? Pressure scanner and pitot probe is there. So the picture of your pitot probe you can see in your slide number 12 of lecture number 28. Link will be in the description. So here, so this pitot static probe has been shown. So this I had drawn also. I had tried to draw. So this is there. Here. Okay. So you can see slide number 12. So how in reality a pitot static probe looks like. For stagnation pressure, we have the front point. Then on the walls of this probe, here you have holes. Okay. That is for your static pressure. Correct. Single channel pressure scanner, pitot static probe, 16 channel pressure scanner. So in your 16 channel pressure scanner, you'll have these 16 channels, right? That are going to give at 16 different locations, right? On the same line, 16 different locations you have, and this is going to give you a pressure data. Nothing special here. Same as it was in your these tubes, right? That we discussed. But here you'll have 16 such tubes. Then a very important instrument, that is your hot wire anemometer. So very minute velocity fluctuations it can get. So it's kind of a probe. Okay, hot wire anemometer, if we talk about. So it's kind of a probe like this. Okay. So this is connected to wire. Okay. So these are prongs, two prongs. Let me check. This is prongs, right? And this is very thin, let's say tungsten wire. Now what happens is, let's say we have some flow happening here. Okay. We have some flow happening here. And then we keep this hot wire anemometer here in between the flow. So because of the velocity, okay, the flow will pass through this wire because of flow. The temperature of this wire is going to go down, right? And this temperature going to go down is going to change the resistance of this wire, right? And this change in resistance this change in resistance of this wire, we get the change in the velocity fluctuations that are happening. Okay, in that region, whichever region we are interested in. So this basically is your hot wire anemometer. And using King's law, we can get the velocity. Okay, so this is there. So 3D traverse system basically is to, so let's say you have this wind tunnel where flow is happening in this direction. So 3D traverse system basically is to move your model. So if you have some model here, let's say this is some model here is installed, right? So we'll connect it to the 3D traverse system, and if you want to move it in the wind tunnel, so we can use this 3D traverse system, right? six component force balance. Okay, so what does this do? So we have, first of all, forces in three directions, right? And then three moments are there. So three forces and three moments, this six component force balance can give. Okay. So smoke and laser sheet visualization, basically to qualitatively visualize the flow, right? Then at the end, performance and characterization. So we want the turbulence to be minimum in the test section. So before using the wind tunnel, we calibrated for that. Okay. And whether the flows and pressures in the test section are coming correctly. So we want to see that also. So this basically is there in this section. This has been discussed. Right. So this is it about lecture number 28. Then questions are there. So one of the works of settling chamber in a subsonic wind tunnel is to reduce the turbulence in the flow. So whether this is correct or not. So this is, I have told. Okay, this is a correct statement. So hot wire anemometry is based on which of the following? So this is based on King's law. Okay. Question number 13. Then two numerical questions are there. So let's see these questions. So question number 14 says that the temperature of a supersonic flow measured by total temperature probe as 570 Kelvin. So total temperature probe, pitot, okay, is, sorry, yes, total temperature probe, sorry, is measuring this temperature. This is temperature as 570 Kelvin. Okay. The probe is having a recovery factor of 0.95. So now the probe has recovery factor of 0.95. Now the flow Mach number is 1.6, for which the isentropic properties having a ratio of static to total temperature is this. Calculate the static temperature of the flow stream. So this we have to calculate. So question number 14. Total temperature from probe is equal to 570 Kelvin. Okay. Now recovery factor is 0.95, right? And Mach is 1.6. Static temperature to total temperature is 0.8047, right? So in that case, your total temperature becomes so let's call it T naught. So T naught becomes static this is there. Okay. So if you see the question, it says that static temperature and flow stream you need to calculate. Okay. Which basically is T infinity. So from your recovery factor formula, so let's call this as T naught probe. So T naught probe minus T infinity by T naught minus T infinity equals to 0.95. This is recovery factor. Okay. Implies, so this is 570 minus T infinity divided by, now T naught is T infinity by 0.8047. Yes. Minus T infinity equals to 0.95. So this is there. Yes. Which implies 570 minus T infinity is equal to 0.95 into T infinity minus 0.8047, taking LCM and then this. Subtracting, we get this. 570 minus T infinity into 0.8047 is equal to 0.95 into T infinity minus 0.8047 T infinity. This is the now calculating these, working out this. So this will come out to be this, right? Then this becomes this. Implies T infinity Now if we calculate T infinity, please calculate T infinity. So this will come out to be 463.21 Kelvin. So this is your T infinity. Okay. So your static temperature of flow stream. Question number 14. The next question is there. It says that a pitot tube is used to measure the velocity of airstream. Gamma is this, R is this, universal gas constant at 25 degrees Celsius and this pressure. If the velocity is this, then the dynamic pressure is this. Now we know that total pressure minus static pressure is equal to half of rho V infinity square. Yes. The question asks about dynamic pressure. So this is your dynamic pressure. Okay. Now we do have, but rho we don't have. Okay. So this is half of rho 4.4 square. So this we have. Then pressure is equal to rho RT. This we have. Right. Now if you see the question, temperature is given, pressure is given for airstream. Okay. So rho RT. T is given, how much is given? 25 degrees Celsius. So 101325 rho into 287 into 273 plus 25. Yes. So implies rho becomes 101325 divided by 287 into 298. So calculating, rho becomes 1.1847 kg per meter cube. So this is your density. Now you have density, so your dynamic pressure becomes 0.5 into So this comes out to be 47. So this will be in pascals. So this was the end of this session. So I'll conclude this session. There were three lectures here. So this was how we take measurements in our compressible flows, right? So we started with the lecture number 26, where pressure and temperature, these two properties were discussed. So in your pressure, we see static and stagnation pressure. So in your subsonic flows, how these two properties are measured. And then in your supersonic flow, how these two are measured separately. So in subsonic, you can do it with pitot static flow, but in your supersonic flow, you'll have to separately get the stagnation, separately get the static pressure because of shock, right? Then uh, in temperature, we saw Seebeck principle and thermocouple based on this principle, right? Thermocouples based on this principle we saw. Then in lecture number 27, there are density-based techniques to study compressible flows. So interferometer, Schlerin technique, and then shadowgraph technique. So these three techniques have been discussed, right? Uh, so your Schlerin technique is in terms of cost, the setup is costly. The setup of Schlerin is costly when you compare it with the shadowgraph technique. One is this. Then in your lecture number 28, subsonic wind tunnels have been discussed. Right? So what is settling chamber, then contraction zone, test section, right? And then how we want the turbulence in the wind tunnel to be minimum. And then there is instrumentation related to it, in which one important instrument is your hot wire anemometer, right? Where based on your resistance changes because of your uh, temperature that gets lowered down because of the flow of fluid or air. So this we saw. So that's it about today's session. So the next session now will be on coming Saturday. Okay. So there we'll be discussing topics related to week number 12, right? And then one extra session is there on Tuesday, coming Tuesday, where I'll just conclude the whole course. So week 1 to week 12, we'll just briefly see the topics that have been covered. Okay. Just get a recap of the whole course in 2 hours. So this is it. Thanks for watching this session. See you in next tutorial. Thank you.